Alrighty, discrete math fans. Here we are back for section 10.2, travel in a graph. I would say out of all the sections in chapter 10, this might be the most important and the most lengthy. Also, probably is the most fun. It's very interesting. We'll look at two different types of circuits and a variety of ways to travel in a graph. So I'll share my screen with you, walking through this PowerPoint. Our biblical inspiration today comes from Galatians 5. You've been called to live in freedom. Freedom is not necessarily what we think it to be. Freedom, we kind of sometimes are told and believe that freedom is kind of the right to do whatever we want. And Jesus, of course, blew that open with love. And love took the opportunity to set aside rights in order to serve. He didn't have to be all that he could have been, I suppose, do all that he could do and have all that he could have. Though he was rich, he became poor for our sakes, that we might become rich. So he showed us that love was greater than freedom, and in his freedom, he chose to serve and put others ahead of him first. And so we don't want to just say, in Christ, I have the freedom to do whatever I want. Rather, we want to say, what does freedom do when it is possessed by love, when its desire is the elevation of the object of its affection and sacrifice? So there it is. That's way more important than anything else in this video. So if that finds its way into your heart and your life, then that will change everything. Okay, let's talk about trails, paths, and circuits. We're talking about movement within a graph, particular kinds of movement, and how that might be useful in different scenarios. It starts out by looking at the Königsberg Bridge problem, a famous 18th century problem that Euler was trying to solve. I think he probably solved it in about 3 seconds. But there were these bridges in this city in Prussia, Königsberg. 7 of them, 1, 2, 3, 4, 5, 6, 7 bridges on a map in this drawing. And the question is, can we take a tour of the bridges, but only go over the bridges once? And if you start looking at this map and thinking about getting from one landmass to another connected by bridges and considering different routes, but wanting to traverse every single bridge, but only once, you might find quickly that that can't be. It's not possible. You could do it twice, but you can't do it once. So we could take a map like that and we could identify the land masses as vertices, locations, and then the bridges as edges, and turn this into a graph theory problem. You can see you just can't do it. You can't do it. And we'll discover why. But you can't do it, and this represents an Euler circuit that we're trying to do, and that would be to traverse every edge in a graph exactly once without repeating an edge. You actually can revisit vertices, but you can't revisit edges. Once you go over an edge, it disappears. And that'll be fun to look at in detail. But before then, let's talk about some definitions, names of different types of movements in a graph. A walk is the most generic kind of thing in a graph, and all you need is a vertex. There are no restrictions on a walk, so pretty much everything is a walk. A closed walk means you start and end at the same vertex. You can repeat yourself on vertices or edges. So closed walk just has one restriction, and that's begin and end in the same spot. A trail is a walk, but having no repeated edge. And a path is a trail with no repeated vertex. I have a Venn diagram of these things in just a minute here, but this is good for the definitions, for the verbiage. A circuit is a closed walk with no repeated edges. So begin and end in the same place. It's closed, and we don't repeat an edge. And a simple circuit can't go back to vertices again in the middle. It can only return to the vertex that it started at. Though our book doesn't define cycle, maybe it's the same thing as a simple circuit. Probably is in a different book. but you can see the relationship between the different types of movement in a graph. And so how do we define travel in a graph? If I wanted to travel from V0 across E1 to V1 to E2 to V2 to E3 to V3 to E4 to V4, that's a lot of words. And if there's a way to say it without ambiguity, then you can say it shorter than that. So if I wanted to get in that movement that I just described, I could just say V0 to V1 to V2 to V3 to V4 and stop. However, if I wanted to go from like V5 to V0 and loop around back to V0 and then to V1, then I would have to either say V5 to E8 to V0 to E10 to V0 to E1 to V1. And because if I just said V5 to V0 to V1, maybe I took that loop and maybe I didn't. I suppose you could say V5 to V0 to V0 to V1. And that might make it, since I repeated the V0, that might make it obvious that something happened in there. But in general, you try to say it as succinctly as possible without ambiguity when you're talking about movements in a graph. So let's practice a little bit. Here's a problem. If these are the movements and we want to define the name of that movement, what would it be? So you can pause the video, look at A through F, and consider the names of the types of movements being described by these different routes. So go ahead and pause the video, do that. That was fast. Here we are. A is a trail, B is a walk, C is a circuit, D is a simple circuit, E is a closed walk, and F is the trivial closed walk, which is just a vertex. So if you have any questions on that, we can talk about it in our Zoom meeting. But hopefully that worked out. There's some practice in the book that's very much like this. In fact, you'll see questions on the homework that are very similar. And all it really is tracing out what's being described and then going back to your definitions and seeing which one fits the best and most specific, of course. We also like to talk about connectivity in a graph. A graph is connected if basically you can get anywhere from anywhere else. If there is an isolated vertex or some vertices that are kind of outside of the axis because there are no edges that get to them, then we have a disconnected graph. Or for example, if this was one graph, all of this, then it would have a connected component right here and then another connected component right here, but they're separate from each other. They're connected within themselves, but if this were one graph, then it's not a connected graph because you can't get to these ones, these vertices from these and vice versa. This is a connected graph because no matter where you are, you could get anywhere else by moving along edges and through vertices. Connected components would be the connected parts of a disconnected graph. So if this whole thing right here is one graph, you can see there are three connected components, and that would be these three vertices connected to each other, these two connected to each other, and these three connected to each other. But within each, there is a disconnect. So the parts of a graph that are connected to each other are called connected components. Three properties from the book, page 647. And these are pretty straightforward. You can always go back and look at a graph and convince yourself of them. We won't prove them, but A is if G is connected, if a graph is connected, then any two distinct vertices can be connected by a path. That's pretty close to the definition of connected. If you are somewhere and you have a connected graph, then you can get anywhere else. Property B, if vertices V and W are part of a circuit in graph G, and you take one edge out of the circuit, you still can get from V to W in that graph. Basically, if you think about it, if you have a circuit, we could just take a circuit like this little triangle right here, and you take out any of the edges of the circuit, you still have the ability to get to all of the other places, but maybe not as fast if that's something in a graph. So that's pretty straightforward, I think. And then C, if a graph G is connected and that graph contains a circuit, then an edge of the circuit can be removed without disconnecting G. So if there's a circuit in the whole graph, you can still take out an edge of that circuit and the entire graph remains connected because the circuit provides some sort of redundancy that you don't necessarily need to get everywhere, although it might have been that you took out something that made the movement more efficient. But we're not talking efficiency, we're talking about the ability. And if you want to, you can draw some diagrams there. You can always push pause and go backwards and investigate a little bit. But I'm going to keep going. This is actually a pretty long section. We're mostly interested in Euler circuits, and that was the Königsberg bridge problem. Though Euler paths are a thing, it's just that a path starts somewhere and ends somewhere else. And an Euler path would use every edge of a graph exactly once. So once you traverse an edge, it disappears. You don't have the option of going over it again. With Euler paths and Euler circuits, you actually can revisit vertices, but once you go over a path, they disappear. An Euler circuit, that's the one we're really interested in. It's a circuit that uses every edge of a graph exactly once. And of course, that means it does also use every vertex, but you can return to vertices. Since it's a circuit, you have to start and end at the same vertex, but the primary objective is to use every edge exactly once. So here we have a graph. If we want to find an Euler circuit, we would have to be able to get, say, from A back to A, covering every edge exactly once. So maybe we go there, 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 back to here, which is okay. I'm repeating C, but I haven't gone over any edge again. So I go back to A, that's where I started, but I haven't finished with the edges. And I can return to vertices, so look at that. I can get all the way back to A. I can cover all the edges. I did have to return to some vertices, but that's okay. Not a problem in an Euler circuit. So really not have a partner, but you can draw a graph. Make sure that it's connected. Obviously, if you have a disconnected graph, you're not going to be able to start somewhere, get back to the beginning, and cover all of the edges. So a connected graph where you can get anywhere from anywhere else, and then try to draw an Euler circuit. You can pause the video for a minute, try to draw an Euler circuit. Some of them are going to work and some aren't. And then the question, of course, will be, what makes it work? And if it works, how do we make it work? And is there anything that we can notice that won't make it work? So go ahead and try that on your own. So here's a graph. It's a little bit more complex. Can you find an Euler circuit in this one? Go ahead and pause the video and try to find an Euler circuit in this one. Well, my guess is you tried and tried and tried. Maybe you didn't try very long, but eventually you probably discovered that you cannot. You cannot. And it turns out that all you really need to look for, see this vertex E, the degree of E is 1, 2, 3, 4, 5, 6, 7. It turns out that if you can find any vertex with an odd degree, you cannot make an Euler circuit. So that's a quick way of kind of scanning through all the vertices and saying, if there's any vertex that has odd degree, I don't keep trying because it's impossible. So that one is impossible. And here's a theorem that goes with that. If a graph has an Euler circuit, then every vertex of the graph has positive even degree. And we won't prove that on the video, but we can sort of talk through it. Essentially, suppose you have a graph and you've got a positive even degree, or you have an Euler circuit. Let's say that. We'll just do the forward part of this proof. If you've got an Euler circuit, that means you start somewhere and you come back to it. So leaving it and returning to it is of even degree. Now, if you have to come back to that in the middle of your circuit, that's okay. Euler lets you return to vertices. But if you have to come back to it before the end, like in the middle of your circuit, then you would have to exit it. So every time you come into a vertex, you have to exit it. And an entrance and an exit, as many times as you do that, contributes an even degree. And of course, the starting point you exit from, and then you return to at the very end. So that contributes a degree of 2. So every vertex of the graph has a positive even degree if you have an Euler circuit. The contrapositive of this, and by the way, this only applies to connected graphs, because obviously a disconnected graph isn't going to work for an Euler circuit. But the contrapositive of this says if the graph has some odd degreed vertex, then it does not have an Euler circuit. So the contrapositive of this takes us back to what we were just talking about in this graph, where we found one particular vertex with an odd degree, and that was enough to just say it's not going to work. The contrapositive is equivalent to the original statement, and the contrapositive of this theorem here from the book disallows an Euler circuit if we have even one, if there exists one vertex of odd degree. This was a for all, if for all vertices we have even degree, but to negate a for all, we get a there exists. So if there exists even one vertex of odd degree, then we do not have an Euler circuit. And this says just as much. So if we look at this, we say, oh, look at C has a degree of 1, 2, 3. Doesn't have an Euler circuit. This graph does not. There's no reason to even try because we found the thing that disqualifies it. Makes it a lot easier. Euler circuits are much easier than the other kind of circuits, which we'll get to in a minute. Those are called Hamilton circuits. So here's a slide where you can do another example problem. Euler circuits. So here's another theorem from the book. If a graph is connected and the degree of every vertex is a positive even integer, then G has an Euler circuit. We sort of just said that, but the interesting thing about this in the book is that it's a proof by construction. It's a proof by algorithm, and the great thing about that is if we look through the proof, it actually tells us how to find that Euler circuit, not just that it's true. So I actually wrote out in my own words, a little bit at least, I used some of the book's words, but I wrote out the proof to this theorem, the construction or algorithm for finding an Euler circuit. So it's a little tricky without an example. I'm going to do an example in a minute, but you can push pause if you want to, and you can read through the algorithm, and then I'll show you how to construct an Euler circuit if you know that there has to be one, meaning that a connected graph has all its vertices of even degree. So go ahead and read those, and then we'll take a look on the next slide at a construction. So here we have a particular graph, and if you want to, you can copy that down. It's on my whiteboard behind me. And what I'm going to do is I'll stop sharing my screen so that you can see the whiteboard. And then we'll talk through just what this algorithm is saying. So the cool thing is, if a graph has an Euler circuit, which means if a graph has all vertices of even degree, it doesn't matter where you start and where you end, because you're going to cover everything, all the edges once exactly. So here's the algorithm. It says pick any vertex V of graph G to start. So I'll just pick, this is called A for the moment, but I'll just call it V. And this will be my starting point. And then it says create circuit C starting and ending at V. So let's just make a circuit. It doesn't have to be any particular one, but here's a circuit. I'll just pick that one. Starting and ending at V, I've created a circuit. And then it says if the circuit is not equal to the whole graph G, which it isn't because there's a whole bunch of the graph left that's not equal to the circuit, then we do something else. Then it says Remove all edges of the circuit from graph G and any vertices that become isolated when the edges of C are removed. Call the resulting subgraph G prime. So what I got to do is I got to take out all these red edges, so they're not included anymore, and isolated vertices. So like this F and this G are isolated once I take those edges out, but then capital C and B are actually a part of the rest of the graph G prime. So I'm going to leave those in there. Continuing on through the algorithm says, pick any vertex W common to both the circuit and G primed. Okay, so what's left that wasn't removed, I could pick any vertex, call it W, common to both the circuit and the remaining graph. So here's W. And then it says, create circuit C prime from G prime, so a new circuit from the remainder of the graph, what's left over, by starting and ending at W. Okay, so I'll start and end at W, and I'll make another circuit. And then it says, patch C and C prime together to create a new circuit, C double primed, like this, as follows. So I'm going to create, actually, I'm going to patch these two circuits together so that they become one circuit called C double prime, as follows. It says, start at V and follow the first circuit until you get to W. So I start at V and I go until I get to W, but then rather than completing the first circuit, I actually enter the second circuit and follow C prime all the way back to W. So I go here, and then I enter the second circuit, follow it all the way back to W, and then finish the larger circuit by returning to V. So my bigger circuit in the patching of these two circuits goes from here all the way back to here. And then basically we repeat the process if we haven't covered the entire graph. Well, we haven't, so the next step would be to remove all of the new edges from the new circuit, the second circuit, and any isolated vertices. So let's see, this is gone now, this is gone now, this is gone now. But the connection to the rest of the graph that I haven't touched yet would be D here and then V still. So what do? We repeat the process. We go to D now if we want to, something that's in common with the previous circuit and the remainder of the graph, and then we make another circuit. And actually we could make another one that doesn't finish out, or we actually could have made the whole one here, but let's just make this one right here, and then we patch the three circuits together in such a way whereas every time you start at the beginning, but every time you hit the intersection of that circuit and the next circuit, you enter into the following circuit without completing the previous one. So I would start here, I'd come up to W, I wouldn't finish this red circuit, I'd enter the green circuit, but when I get to D, I'm gonna go through orange till I get back to D, and then I'm gonna finish green circuit, and then I'm gonna finish red circuit. And if that didn't do it, then you do it another time. So you can see that there would be one more circuit, and this would be the last one here. And so we would remove these edges, but we would retain this edge, remove these vertices, retain this vertex because it's in common to the remainder of the graph that we haven't used yet, as well as the circuit that we just created. And then that becomes a new pinpoint whereby we can create another circuit. And finally, you can see in this problem, we're going to be able to get all the way through. So you start at the beginning, you start traveling the circuit, but when you hit the next circuit, you enter the second circuit before completing the previous one. Oh, I hit the next circuit, so I enter that. Oh, I hit the next circuit, so I enter that. And I finish that last circuit, and then I complete the previous circuits that I hadn't completed before so that I can get all the way back to the beginning. So that's an algorithm for finding an Euler circuit if you know that one exists. And you will know because, again, the theorem says that if all the vertices are of even degree, then you do have an Euler circuit, as long as the graph is connected. So that's really cool and helpful. Let's go back to the PowerPoint. I'll just briefly mention Euler trail. Euler trail is just like an Euler circuit, but you start and end in a different place. So there's a couple of practice problems in the book. I've got a couple here. Simply starting and ending at different places. And actually that means that the beginning and the end place, if they're not the same, if it's not a circuit, then those would be the only two vertices with an odd degree, and you would have to go there. So if I was going to do it here, C has odd degree and D has odd degree. If I wanted to do an Euler trail, I would have to start and end at C and D, and all the rest would have to have even vertices. It's a fun little problem. Finding your way through a maze, which essentially would be an Euler trail. I suppose if you did so most efficiently and began and ended in different spots. So that'd be an Euler trail. And there's a solution to the previous problem. Another very interesting type of circuit that's very useful is called a Hamilton circuit. So some of you maybe know a little bit about the history of this. Actually, it has nothing to do with Alexander Hamilton, has nothing to do with the musical Hamilton, but those are fun too. It has to do with an Irish mathematician, Sir William Rowan Hamilton, and a puzzle that he was trying to solve, taking a dodecahedron and actually kind of flattening the whole thing and turning it into a graph. Well, the kinds of graphs that we're talking about. And with a Hamilton circuit, we want to pass through each vertex exactly once. We want to start and end at the same spot. It's a circuit. And we don't care if we traverse all of the edges. So it's not the same as Euler, but you can see maybe there's a little bit darker lines in here. I think they are. Maybe it's my next slide. I can't see them now. I'm getting too old for this. Is there a circuit that passes exactly through all of the vertices? You don't have to cover all the edges, but returns back to where you started. The motivation behind this puzzle was that he wanted to travel to all these different cities without returning to a city again. And eventually what we'll want to do is we'll want to do it the most efficient way possible. So it's called the traveling salesperson problem. We'd like to travel to every vertex, and there'd be a weighted graph like distances between cities in the most efficient way possible. Yeah, this one's the one I was thinking of. You can actually see a Hamilton circuit here. You can start wherever you want, but the blue lined edges are not included. But if you follow the black lined edges, you can start wherever you want. Start here, wrap around, just keep following the black lines. You can see if you follow the black lines, and get all the way back to where you started. So this graph does have a Hamilton circuit, and he used it with these cities. So of course there is a Hamilton circuit in this case, but there are no numbers in between the cities to represent distances, and that becomes a more interesting and complicated problem if you want to like minimize the Hamilton circuit. And there's actually no mathematically known way to do that in an optimal way without trying all of the possibilities and picking the least one. Here's another slide that just shows you a Hamilton circuit. Again, you got to cover all the vertices. You got to visit every single vertex, not every single edge. Notice with these Hamilton circuits, essentially the Hamilton circuit is a subgraph. It's a part of the full graph. And you can miss out on some of the edges. They don't get squiggly lines. But once you have this, think about it. Every time you visit a vertex, you get in and then you leave and you don't come back. So the subgraph at every vertex has a degree of 2 because you just enter and you leave. And again, it's fine to leave out edges. Hamilton circuits. Here's an example, another example of a Hamilton circuit. You cover all the vertices, you visit them all, but not all of the edges, which means the red subgraph has vertices with degree 2. You can practice this one if you want to. This is actually pretty easy. You can find a Hamilton circuit here. Just wrap around. You got to get back to where you started. You got to hit all the dots. You can skip as many edges as you want. You can't revisit dots. There are some more practice problems, which you can pause the video and practice on if you want to. So how do we compare these Eulerian and Hamilton circuits? There's a slide kind of showing some graphs that do and don't work in the different scenarios. I accidentally flipped those slides around. Alexander Hamilton is the only non-president to be on U.S. currency. Is that right? I think so. And I think he was he an economist? He was into finance. Supposedly he was pretty brilliant, and maybe our country would have turned out a little bit differently if he hadn't gotten killed in a duel. So that was too bad. But again, not the same guy at all. The mathematician was long gone by then. We've talked about the difference between Eulerian circuits and Hamiltonian circuits. So just make sure that you understand this page and you understand that the mathematics and the applications behind these two types of circuits is very different, because with Euler circuits, we can look at a graph and we can quickly know if it will work or not. And then if it will work, we have an algorithm that will find the Euler circuit for us. But Hamilton, at best, is like educated guesses and trials and errors. And, you know, if you can find an algorithm that will find a Hamilton circuit, especially an efficient one, an optimal one on a weighted graph, then you can probably get your honorary PhD and make a lot of money, but no one has done that yet. So we are relegated to computer programs and trying lots of options, educated guesses, you know, so we don't have to try all of the options, but wish that there was a better way of doing things. If a graph has a Hamilton circuit, then there is a subgraph with the following properties. We sort of discussed this verbally a little bit ago. Of course, the Hamilton circuit, the subgraph, contains every vertex of G. Of course, it is connected because you got to get from everywhere to everywhere else. It has the same number of edges as vertices, and every vertex of the Hamilton circuit has degree 2, which means if any one of these properties is not true, then the graph does not have a Hamiltonian circuit. So that's kind of a way that we can look at a graph and not have to keep checking. If we can find that there's a violation of one of these properties in any way, if we have a disconnected graph or something like that, then we would know. Don't even keep trying to find a Hamilton circuit because you won't. Neither of these two graphs work. Remember, if a graph has a Hamiltonian circuit, then there's a subgraph where the degree of every vertex is 2. So like, for example, graph G here, this vertex has a degree of 3. So you'd have to take out one of the edges. And if you took out this edge right here, for example, then C would only have a degree of 1. So what edge do you take out of these 3 without creating a problem? You take this edge out, then E is disconnected. That's not good. In this graph over here, you have to find a subgraph where all the degrees of the subgraph are 2. Well, there's a degree of 4 here, so you would have to take out 2 of those edges for your Hamilton circuit. But if you do, pick any 2 you want, pick any one, and that becomes problematic. If I take out this edge, then A only has a degree of 1. So you can see that there is a problem in taking out some edges that you would have to, because you have to end up with 2 at every vertex in your Hamiltonian subgraph. So that's a nice way of knowing that it doesn't work. Interesting problem is the traveling salesman problem. The traveling salesman wants to save as much money as possible, wants to visit all the cities that he visits to sell his goods, and wants to take the most efficient route possible. So you end up with a weighted graph. Salesman starts here, needs to cover every city, but wants to do it in the most efficient way possible. This one should be pretty easy to find because you don't have to try a lot of things. But this is a weighted graph, and if these are like distances between cities, or maybe they're like costs to get from one city to another, weights can be whatever unit is interesting to you and relevant to the application. But when you get to a little bit more complex problem, like this one, we start at city one, we return to city one, we got to cover all the other cities, and then how do we do that in such a way that we minimize the total weight if we add up all the edges together? And as I recall, students have played with this one. I think, what was it, 62 or 63 maybe is the smallest total weight. So you can pause the video and try to get from one all the way back to one, covering all the vertices and adding up edges along the way in the best way possible. That's the traveling salesperson problem. It's a Hamiltonian circuit problem on a weighted graph. At present, there is no known algorithm for solving the traveling salesperson problem. So we have to use brute force, which means try every route, or we have to make a lot of educated guesses, or we have to just try to find one that's pretty good and seems to beat all the other ones that we try and call it good enough. But it's kind of frustrating to have problems like this in mathematics that you just can't quite solve as well as you'd like to. And that's it, 10.2. Lots of stuff. I went fast. Make sure that you watch this video and come to class in our Zoom session with questions after you've tried some of the homework problems. Let me know what problems you have beforehand so that I can best be prepared to serve your needs. Hope you have a great evening, and I will see you soon.